Next question is, an electron and a photon have the same wavelength of 1 nanometer. Find. Part A is their momentum. Because relation between the wavelength and the momentum is given by the relation lambda equal to h by p, or we can write momentum is h by lambda. Because wavelength of the electron and photon are given same of 1 nanometer, that means it is 10 raised to power minus 9 meter. So their momentum will also be same. Substituting the value, h is the Planck's constant having the value 6.6 into 10 power minus 34 joule second, and wavelength is given 10 raised to power minus 9 meter. So solving it, it will be 6.6 into 10 raised to power minus 25 kilogram meter per second. So this will be the momentum of the electron as well as the photon. Part B is the energy of the photon. We know energy of photon is given by E equal to h nu, or we can also write it is hc by lambda. We are given lambda. So substituting the value, h is the Planck's constant having the value 6.6 into 10 power minus 34. C is the speed of the electromagnetic wave and its value is 3 into 10 to the power 8 meter per second divided by, and wavelength is given 10 raised to the power minus 9 meter. And now on solving we will get the energy in the unit of joule. To get the energy in terms of the electron volt, we have to divide joule by the value 1.6 into 10 to the power minus 19. So we will get 6.6 into 10 raised to the power minus 34. It is the Planck's constant value. 3 into 10 raised to the power 8. This is the speed of the light, and the wavelength is 10 raised to the power minus 9. This joule amount is divided by the conversion unit, that is the 1.6 into 10 raised to the power minus 19. So we will get the energy in electron volt. We know 1 electron volt is equal to 1.6 into 10 raised to the power minus 19 joule. So solving this, we will get 1240 electron volt, or we can also write it as 1.240 kilo electron volt. Here it requires some calculation. We can calculate the result directly if we remember the value of the product hc, because h is the Planck's constant, it has the fixed value. C is the speed of electromagnetic wave or the light, it is also having the fixed value. So this product will have the same value, and it is 1240 electron volt nanometer. So we have to remember this conversion for hc. This hc has the value 1240 electron volt nanometer. Therefore, substituting the value here, E will be equal to hc by lambda. Hc has value 1240 electron volt nanometer, and wavelength is given 1 nanometer. So substituting the value of the wavelength in nanometer. So we will have this nanometer and nanometer get cancelled. Therefore, we will have 1240 electron volt, or it is 1240 kilo electron volt as we have calculated above. In part C, the kinetic energy of the electron. We know that kinetic energy has a relation with momentum as k equal to p square by 2m. Here m is the mass of the electron, p is the momentum of electron. We have calculated that momentum of the electron is 6.6 into 10 raised to the power minus 25. So we calculate here it is 6.6 into 10 to the power minus 25 square divided by 2 into mass of electron, that is 9.1 into 10 to the power minus 31, and this kinetic energy will come into the joules. So to calculate in electron volt, we have to divide this joule by the conversion factor 1.6 into 10 raised to the power minus 19. So we will have 6.6 into 10 raised to the power minus 25 square divided by 2 into 9.1 into 10 to the power minus 31 into, and the conversion unit is 1.6 into 10 to the power minus 19. So this much of the electron volt the kinetic energy will have, and on solving we will get 1.51 electron volt. Next problem is calculate the de-Broglie wavelength of the electron orbiting in the n equal to 2 state of the hydrogen atom. Here, the cell in which the electron is revolving is the second orbit. And for revolving electron, we know that for stable orbit, the angular momentum of electron Ln is equal to mv of the electron in nth orbit into r is the radius of nth orbit, and it should equal to the n times of h by 2 pi. This relation is obeyed by the electron for the stable orbit. That means the waves are the standing waves. This implies that if we see this mvn is the momentum of the electron in the nth orbit, so pn into rn equal to n into h by 2 pi. This implies that this 2 pi rn, if we cross multiply and taking this pn on the right hand side, so we will have h by pn. This implies that because we know de-Broglie wavelength lambda equal to h by p, so this h by pn will be the wavelength of the de-Broglie wave in the nth orbit. Therefore, we can write 2 pi rn equal to, there is n is also here, n into lambda n. So this is the condition for the electron revolving in a stable orbit as per the Bohr concept. Using this relation, we can calculate the de-Broglie wavelength when electron is orbiting in the n equal to 2 state or the orbit. So for n equal to 2, we know the radius r2 will be equal to, in general, Rn, that is the radius of the nth orbit, will be equal to the n square times of a basic value, that is parameter, that is R0, and this R0 has the value 0.53 angstrom. So radius of second orbit will be 2 square into R0, that is 4 into 0.53 angstrom. Using this value, we can write 2 into pi is 3.14 into Rn is 4 into 0.53 angstrom, and this is equal to n is 2 because it is given, and we have to find the orbit wavelength of the de-Broglie wave in the second orbit. So lambda 2 will be equal to, this 2 get cancelled, simply 3.14 into 4 into 0.53 angstrom. This is equal to, if we calculate this in nanometers, we can also write it as 3.14 into 4 into 0.053 nanometer. If we simplify it, we will get 0.67 nanometer. This is the wavelength of the de-Broglie wave for associated with the electron orbiting into the second orbit.